Hello everyone, my name is Kazem Vakizadeh, PhD student of Petroleum Engineering at University of Calgary. Thank you very much for watching my presentation for Energy Simulation Summit 2024. My research is about simulating two-phase flow using pore network modeling. As you know, understanding two-phase flow in porous media is essential for optimizing oil recovery methods. For instance, if we know the behavior of water and its interactions with oil, we can predict oil recovery for processes like water flooding, and PNM models are among the most popular methods for such simulations in pore scale. Usually, pore network models or PNM models are based on solving flow equations in networks containing pore bodies and pore troughs, which try to mimic the real porous media. And we should note that although static pore network models are very useful, they struggle with capturing complex flow phenomena like fingering, where water channels through the oil. And the reason for this is that these kinds of phenomena are usually based on transient behavior of fluids. So we need some dynamic pore network models which allow us to learn these behaviors in greater detail and offering insights that static models cannot. Based on these, dynamic pore network models are essential for these cases, but most important limitation of such models is high computational cost, which limits their scalability for large networks. And to solve these problems, researchers have focused on some high-performance computing methods. High-performance computing, or HPC, refers to some parallel processing techniques to solve complex computational problems quickly and efficiently. And in our case, it allows us for faster simulation of pore networks at larger scales. So the main goal of our research is developing a dynamic pore network model by using high performance computing methods for assessing two-phase flow in porous media. And to do this, we will start with a network generation. This network generation can be based on synthetic data or based on real images from porous media, for example, CT scanning images. And results shown here are based on a synthetic cubic network, and we use that to only assess our procedure for dynamic invasion percolation. The heart of our algorithm is the code for assessing invasion percolation in a dynamic method, and to do this we have used a one pressure approach. Actually, we made a Q array in which we have used a binary heap structure, and in this structure we will give the troughs with highest priority the upper place, and as we go down in the structure, the priority of the troughs to be invaded will be lower. So to have a dynamic method, we have defined a potential function based on capillary pressure of troughs and pressure of invaded pores in each step of invasion, and troughs with which are available and have a higher priority will go upper in this structure. In each invasion step, we will check such an array, select the trough that should be invaded, then invade the next pore connected to that trough, and update our pressure distribution. This section, which is updating the pressures in each steps, causes high computational load to our algorithm, but we try to make our algorithm in a sequential and parallel method that we can use HPC methods for faster calculation. After updating pressure in each step, we will update our Q structure and repeat this procedure. I have brought some results to show here, just as an example. The first one is the structure of our network. As you can see, pore diameter distribution is around 2 to 8 micrometer. In addition to that, we have tested our algorithm for these, and we have seen invasion pattern at different invasion steps. For each of these, we have the pressure distribution of invaded pores, and as you can see, some pores will be trapped during this procedure. Based on the results of our invasion algorithm, we can do some special core analysis, for example, finding relative permeability curve or PC curve, and you can see that entry capillary pressure in this case is something around 40 kilopascal. The results that you see here are based on this dynamic algorithm, and we have tried to simulate a drainage process in which our porous structure is oil wet, and we are flooding it with water. Now we are developing such a sequential algorithm for imbibition, and we are working on making it faster with CPU based and GPU based HPC algorithms. Thank you very much for watching my presentation.